Euclid's Elements, Book 2, Proposition 12. In obtuse angled triangles, the square on the side subtending the obtuse angle is greater than the squares on the sides containing the obtuse angle by twice the rectangle contained by one of the sides containing the obtuse angle, namely that on which the perpendicular falls, and the straight line cut off by the perpendicular towards the obtuse angle. We'll have our obtuse angled triangle. We'll call it a B, C, and then we also drop our perpendicular and extend outside AB, so that is a perpendicular. What we want to show is that the square on CB is, well, we're going to show this, but then I'm going to write up what our actual to prove is. The square on CB is going to equal the square on CA plus the square on AB plus twice the rectangle contained by BA and AD. Which means that if we took away the rectangle, twice the rectangle, then the squares on CB, which is the square on the side subtending the obtuse angle, that would be CAB. The square on CB will exceed the squares on the sides containing the obtuse angle by that amount. So to write up our actual to prove, it's a more or less an inequality. We would say that the square on CB is greater than the squares on CA plus AB by this amount, by twice the rectangle BA AD. Step 2. We know from Book 2, Proposition 4, that with this straight line BD cut at random at A, that the square BD is equal to the squares on DA plus AB plus twice the rectangle contained by the segments, namely BA and AD. We're going to add the square on, sorry, we're going to add the square on CD to both sides of step 2. Therefore, we get CD squared plus BD squared are equal to CD squared plus DA squared plus AB squared plus twice the rectangle contained by BA AD. Step 4. But if we look at the right triangle DCB, we can see that the square on CB is going to be equal to the square on CD and DB. That's by Prop 47. So I can rewrite that, or show that that is equal to the square on CB. And then if we look at the smaller right triangle CDA, we know that the square on CD plus the square on DA will equal the square on CA. Therefore, I can rewrite this as CA, square on CA, and then I've still got this over here. So I've got my square on AB plus twice the rectangles contained by BA, or twice the rectangle contained by BA AD. But we can see that this is exactly, step 4 is exactly what we've got in our step 1. So that if we subtracted twice the rectangle BAAD, then we would get this situation. CB would exceed the squares on CA plus AB by exactly twice the rectangle contained by BA, AD. And the square on CB is the square on the side subtending the obtuse angle. The squares on CA and AB are the squares on the sides containing the right angle. Sorry, the obtuse angle. Q, E,